Good afternoon, dear students. Our next topic is degrees of freedom. We can give a definition for degrees of freedom as the total number of independent ways in which particles of the system can absorb energy. It can be explained in a way like you consider a molecule, just a molecule, let it be a gas molecule in space. That means it has this is x axis, y axis, and z axis in a space. It can have a movement, it can move in the x direction, y direction, or in the z direction. So this is free to move in all the three directions. So I say it has a degree of freedom 3. So these are the three independent ways in which this molecule can move. But if there is a restriction, like this molecule, it is fixed to certain axis. For example, instead of a single molecule, I take two molecules which are connected here. Just they are connected. Two molecules I take, they are connected here. So together these molecules it has freedom to move in all the directions. Like these two molecules, they can move in all possible direction. This molecule can go in the x, y, z 3 direction. This molecule also can move in the 3 direction, x, y, z direction, but they are under a constraint. They are bounded with a bond. They are under a constraint. There is a constraint here, which means there is some shortage for its movement, some restrictions for this movement. So for example, if it is an atom with one molecule alone, just a one molecule alone, without any without any constraints, it has three directions possible for its movement, which means I say if an atom has n particles, it has 3n freedom, 3n degrees of freedom. So depending on the barrier or restrictions or constraints, this freedom will decrease. We write this degrees of freedom as an equation that is 3n minus k, where n is the number of particles present in the system and k is the number of relations or constraints or restrictions in this. So with this, let's analyze different cases. For a monoatomic gas, a monoatomic gas means a gas with just one atom in that. Just one particle is present in that. So we put n as 1. And if we do not mention any constraint, that means there is no restrictions for its movement, then k is 0. So as per the equation, F is equal to 3n minus k. As there is no restriction, k is 0 and the number of atoms present is 1. So we get 3 as the degrees of freedom. But for example, if it's a diatomic gas, n is 2, but as a diatomic gas means they are bounded by a line, maybe at least a line I can say. So in that case, there is a constraint, there is one constraint, k is equal to 1. In that case, if I put this equation, I say it has 5 independent directions in which it can move. In 5 different ways it is free. Its movement is free over 5 different ways. So that's the concept of degrees of freedom. Similarly, I take a triatomic gas, that means 3 atoms are there. They are at least bound by 2 restrictions. These are not freely movable. At least 2 bonds are there. They will be under a restriction, that is k is 2 in this case. So substituting this, I get a 7 as the degrees of freedom for that. So it may not be always like this. A triatomic molecule, it can be a linear one. This is a linear triatomic gas. That means these molecules are arranged in a line. That may not be always the same case. It can be a planar one also, a triatomic gas, like this three atoms but they are connected, and there is a planar structure in which there are three constraints like this. It means one is this, another one is this, another one is this. Three constraints are there. In that case, this freedom reduces to 6. Now, related to these degrees of freedom and energy of a particle, we have a rule, that is law of equipartition of energy. This is about the energy of molecules and under some considering the degrees of freedom. So it states that in any dynamical system in thermal equilibrium, suppose any system is in thermal equilibrium, the energy is equally distributed among its various degrees of freedom. And per molecule, every molecule, the energy distributed will be half kBT per degrees of freedom. We have already seen this equation, that is kinetic energy K is equal to half kBT. This was derived by considering that one molecule is present and it has 1 degree of freedom. So here per unit, per molecule, per degree of freedom, the kinetic energy is half kBT, where kB is Boltzmann constant and T is the temperature, absolute temperature. Instead of that, let us generalize this equation, that is this half kBT we can consider the degrees of freedom. Then this kinetic energy equation become F times half kBT, where F is the degrees of freedom in each case. So this is per degree of freedom per unit molecule or per molecule. Otherwise, if it is considering all the degree of freedom, we have to write it as K is equal to F times 1 by 2 kBT. So using this, let us analyze the different cases for monoatomic gas, diatomic gas, etc. The energy. For monoatomic gas, we told the degrees of freedom is 3, which means K is 3 times 1 by 2 kBT. F is 3 in this case. F times 1 by 2 kBT, we get 3 by 2 kBT. Now for the system of 1 mole, suppose this is for 1 molecule, if it is for 1 mole, the equation become 3 by 2 n times kBT, where n is the Avogadro number. N kB is nothing but the gas constant R, because we defined kb as kb we defined as R by n, which means our K is 3 by 2 n kBT will become 3 by 2 RT. So we got the kinetic energy K is equal to 3 by 2 RT for a monatomic gas. Now we told these all are perfect gases. That means there is no potential energy between the gas molecules. Then the kinetic energy is the total energy, that is the internal energy of this gas. Internal energy of this monatomic gas is 3 by 2 RT. This internal energy, if you differentiate with the temperature, we get it as Cv. We have already done this. Cv is du by dt. So that will give you Cv as 3 by 2 R. Hope you remember Cv. Cv is the specific heat capacity at constant volume. Molar specific heat capacity at constant volume, that you will get as 3 by 2 R. And we had also one more relation, Cp minus Cv is equal to R. That is Cv you give it as 3 by 2 R. Then we get Cp is equal to 5 by 2 R. We had a term called gamma, that is the ratio of Cp and Cv, which will give you 5 by 3 as this. Similarly, for a diatomic gas, if you take the F value, the degree of freedom was 3n minus k, which was 3 into 2 minus 1, which means 5. We will get F is 5. So same way, if you go this energy, internal energy, you get it as 5 by 2 RT. Then CV will be 5 by 2 R, and also you get CP as 7 by 2 R. CP is R plus CV, which will give you 7 by 2 R. Gamma will be 7 by 5. So that is gamma value CP by CV for a diatomic gas. For a triatomic gas, we told F is 7. If it is a linear triatomic gas like this, linear triatomic gas, we had two constraints, K is 2. So F is 3 times 3n minus K becomes 3 times 3 minus 2, which is 7. So for linear triatomic gas, it will be F is equal to 7. Kinetic energy will be, which is the internal energy, that is 7 by 2 RT, which will give you CVS 7 by 2 R, CPS 9 by 2 R, and gamma S 9 by 7. This is for a linear triatomic gas. For a planar triatomic gas, F was 6. We told this was 3 structure. That means we have a constraint as 3. So F will be 3 into 3 molecules minus 3, which will give you 6. So 6 by 2 RT will become, and the CV becomes 6 by 2 R, and that is 3R. 6 by 2 is 3. CP will give you as 4 by 4R, which means gamma is 4 by 3. If it is polyatomic gas, like many, degrees of freedom becomes F times 1 by 2 RT. Then CV will be F by 2 R. CV will be F by 2 R, and CP will be 2 plus F by 2 R, and gamma will be 2 plus F, 2 by F plus 1. So these are the different values of degrees of freedom, and these equations alone you can take. You need not study this derivation and all. And what you can do is you can study for these numbers alone, all these final results alone, gamma value or CP value, CV value for different kind of molecules.